Is this working? Yes. Okay, so we've done the individual subject analysis, and we have inside the analysis folder these T maps and the contrast maps. Now in SPM we take forward the contrast, which are the difference between the betas. Okay, so this is the estimate of the magnitude of the difference between two betas will be taken forward to then do group level analysis. Now, when we do a first level model, what we're doing is we're assessing the degree to which a brain region is activated within a subject. And our inference is limited to that subject. If you want to draw information about, or inference about the population from which the subject is drawn, we need to have a different statistical model, one that takes into consideration the sources of variance, particularly the between subjects variability. And that's implemented in SPM using the random effects analysis. So what we're going to do is we're going to basically take the contrast images from a group of subjects and do some basic models in SPM. So if you're inside SPM course 2017, ULS, you should see a folder called cons for group level. So let's change directory into there. So there's three folders here. One which is ROIs. If we change directories into ROIs and list ls, you see the same three masks that we've used previously. If you see into models, you'll see some batch files that I've previously created for various group level models. One sample t-test, two sample t-tests, paired t-tests, multiple regression, one-way ANOVAs, one-way ANOVAs within subjects, so repeated measures, one-way ANOVAs, full factorials where the groups are independent. So let's say two groups and then two genotypes, for example. So actually it's four groups, but they're related, two factors related. And then finally, flexible factorial model, which is the most complicated model, which allows for multiple repeated measures designs. You can use these models to inspect things and get a feel for how you set things up, but they won't actually execute because the paths are incorrect probably. So let's click on here. If we then go into cons for group level models, we'll see, let's see, one sample t-test. Where's one sample? Oh, one sample t-test. This is the setup for one sample t-test. Okay. And the scans are listed there. So the problem is the paths are incorrect here. So you can use them to inspect if you want, to get a feel for models if you're trying to set them up. In this case, we're going to set them up by hand. So first things first, let's go up one level. And we'll go into data for scientists. Sorry, data for second level. Sorry, my brain's elsewhere. If we list, you'll see there's four folders. One called placebo 1, one called placebo 2, drug 1, drug 2. So this was a study where we used the same motor task, but individuals came in on 4 visits, for 4 visits. On 2 of those visits, they received a placebo. On the other 2 visits, they received one of 2 drugs. So they did have 2 separate drugs. We're going to focus primarily on placebo 1 and drug 1, and then for the more complicated models, you can expand out to the other ones. Okay, so let's begin. We need to create a folder. So let's make a directory called one sample T. Okay. And this is going to allow us to test for activation. Just on average, over a group of subjects, is what regions show a significant recruitment for a contrast. Now, if memory serves, these contrasts are all motor greater than control. So it's this contrast here, 1, 1, minus 2, but for 16 subjects. So let's click on specify second level here, and then go to the batch. So again, the first thing we need to do is specify a directory. So we click our one sample. And then in the scans, we select all 16 files we're going to need. So specify. Let's go into placebo 1. And if you right click, we can select all. So you can see it's con1, subject 1, subject 10, all the way through. So we'll select all of these. So that's 16 files. You can include covariates here. So if you click covariate, if you basically the vector, you have one value for each scan. So let's say you want to control for IQ or age or something like that. You give it a name. Interaction, again, mean centering. If it's an useless covariate, just leave it like that. So that's normal. So delete that covariate. We don't want to do that. Masking, again, not really necessary in this case. You can adjust the thresholds. You can have an absolute mask, but it tends not to be used for fMRI. Implicit mask is standard. It basically, at the group level, it only includes voxels where every subject has coverage. So if you remember, at the first level, we used that, we created an implicit mask based on the threshold of 0.8. So everyone's mask will be slightly different. And this implicit mask here basically says, if any subject is missing coverage in a region, that region's out of the analysis. Some other software can allow that, not full coverage across all the subjects, but SPM insists on it. Explicit mask means you can add a mask where you can spatially constrain it. So let's say you don't want to implicitly mask the data, you can say no, and let's say I want to explicitly mask it with the basal ganglia, for example. So we go back to our ROIs. And that'll basically only test voxels in the basal ganglia. But I don't want to do that. And I have a feeling I might have caused myself more grief by doing that than anything else. Maybe I can clear a variable here. Right click. No, I see. I've caused myself grief now. That was a mistake. So I'm going to have to start this quickly again because... there we go. Yeah. So it doesn't allow you to clear that once it's been created, once you've created that variable. So again, I've selected the directory. I'm going to go into placebo1, select all the scans. So I've done covariates, multiple covariates. Again, you can load in a text file or a map file that has multiple covariates saved if you want. If you want to do lots of different models and you just want to keep loading the same things in. Again, global calculation, we don't use that. A lot of these things here are remnants from PET. They're not used so much anymore. Although for VBM, you can often include the global normalization. You include the total intracranial volume as an ANCOVA. Okay, or just often is just as a covariate is the other option. Okay, so we'll do the same thing. We'll add on the model estimation part here. Click dependency. And then we'll save this batch. We'll save it inside the folder as one sample. Okay, and we'll press play. This is usually quite quick. I'll pause it just in case. Is it back? And it's recording. Yes. Okay. So that actually didn't take that long. So here we go. Model is estimated. The model's been created. Now, this sometimes throws people, but the model for one sample t-test basically is like this. It's just the mean response. You can see it says here mean over all the subjects. So there's a single constant, a bit like the intercept. Okay? So we've got the map here. Now let's test some inference. We need to create a contrast and we need to correct for multiple comparisons. So one sample t-test, pick your spm.mat, and the same procedure over and over again. This is identical to the first level model in terms of the interface. So for this model, there's only one column. Okay, so we can have activation. So that's basically 1 times the mean. Or we can have deactivation, so regions that go down, i.e. they're more active during control than they are during motion, and that would be -1. Okay? In this case, we're going to focus on activation, so we'll leave it at 1. Ooh, sorry. So submit. And press OK. Press done. Apply masking, we'll say no, but again you can, but if you remember, that will just spatially constrain the map. it won't change the statistics, they'll still be whole brain statistics. So we'll play none for P adjustment, pick a high threshold. Now it's important to note, I should say, that with cluster correction you can adjust this threshold, but it's generally considered bad form now to reduce that threshold below the default. Paper by Torwager, and there's another one, it evades me at the moment, but suggests that you increase your false positive rate by reducing your high threshold for cluster correction, or what's called a cluster forming threshold. Okay, so here's our map. Let's overlay it on a brain again. So let's go, so you can move to where you want to, here, let's say, and then click on overlay slices. Oh, and then it'll ask you then what do you want, so again, what do you want to overlay it onto. So we go to click on previous, go to the top, SPM, canonical, get a response. But let's click on sections. Now, because we've done sections before, I'll do it one more time. Go to previous, SPM, canonical, like that. We now can click around here. But once you've done that before, you can then just do previous sections. Or did we do render before? Previous render? Yes, we did. Okay. So once you've done it once, it remembers that that's where you want, what the file you want and the options you want. So you can just select previous. Now, there is the option to render as well. But one of the options is, rather than rendering using, let's go to SPM, you can just go into render and pick one of these images as we did before, and that's what this is from. But there is also the option to go back into canonical, and you have these cortical surfaces. Now we'll pick a small one, 8196 I should say. And what you get is the blobs overlaid on a nice brain that you can then rotate. Hopefully. Now this is more intensive on the servers and stuff, so you want to risk. But it does have one nice feature you can do, which is right click. Oh, no. Let's go to, if you right click, oh no, there used to be an option to, undo that. That wasn't so good. That's better. Well, there used to be an option to inflate this. I'm very disappointed. The glass brain used to inflate. Oh, that gives you more freedom. But I'm disappointed. Sorry, I was hoping to show you the rotated image. Sorry, the inflated image. Oh, sorry about that. Okay, so let's go back to the statistics. So again, you can always do file, save as, and this will save that as a JPEG or something like that. JPEG or TIFF or anything like that. That's this whole, but it'll save the whole graphics window. So let's say JPEG, cancel. Save this whole graphics window. So now we need to go over multiple comparisons of correction again. So let's go to here. So multiple comparisons correction, it's very important because we know we're testing 200,000 voxels. There may be many false positives. Now the standard approach will be bond-friendly correction, which is to divide the critical alpha 0.05 by the number of tests, but that's far too conservative. Although in reality, because we smooth the image and things like that, there isn't really 200,000 independent tests. Adjacent voxels are highly correlated and they're not really independent of each other, which is why we use Gaussian random field theory, because it uses that smoothness to tell us how many independent elements there really are in the map. And then we threshold the maps such that there's only a 5% chance of there being any false positives. This is the glass brain. So this is just explaining cluster correction again. And oh, sorry. So if you think about like a T map as like an undulating mountain range, we have some regions that are very lower amplitude but have a very large spatial extent. Some that are very wide. Sorry, very high amplitude response, but relatively narrow. And then there's other ones. So set level just would say there's 3 peaks crossing my threshold. This would be the uncorrected threshold we'd set. Is that significant? Would I expect that to happen by chance? Cluster level correction says, for this threshold, would I expect something of this size to happen by chance, or this size to happen by chance, or this size to happen? And it would go, okay, yeah, this is all within normal range. This is probably not significant, but something of this size doesn't happen by chance. This is a significant result. So I have multi-comparisons correction on the basis of cluster extent, because it wouldn't happen by chance. And the algorithm is basically just calculating the likelihood of a cluster of this chance happening, given this high threshold and the intrinsic smoothness of the image. The peak level correction doesn't really care because what we're about the spatial extent, but it's asking whether as I keep raising the height threshold, I just raise it until I know there's only a 5% chance of there being anything on the map, and therefore there's only 5% chance of a false positive. And this is explained in various sources, but in essence that's what we're doing. It's still quite a conservative approach, peak level correction, because there's only 5% chance of anything being on the map. But by there only being 5% chance of something being on the map, there's only 5% chance that it's that any of them are false positives. But it's still quite conservative. So that's what we're doing. So in cluster level correction, set level correction, we pick an arbitrary threshold and then we calculate whether the spatial extent or the number of clusters would be likely to happen by chance, and we adjust the map accordingly. For peak level, we keep raising the floor until we're at a level where we can be confident we wouldn't expect there to be, there's only a 5% chance of anything being on the map, and therefore only 5% chance of a false positive. Okay, we've covered that. Okay, so we've got a map here. So let's just, the first thing to do, let's correct for multi-comparison on the basis of cluster of peak response, and it's very simple. You go contrast, significance level, set to 0.05. And that's your map. Okay? And you can save that map. I'm sorry, save. As a threshold in SPM. So we'll call it activation. You can right click here, print text. You can export to CSV, although in my experience that doesn't always work very well, so I just print to here. And then I usually just highlight all of it and copy and paste into Excel. I have Excel open on the side. Now, we'll worry about plotting when we get to the next one, because the plot of this will just be a single bar, which we don't really care about. It's not particularly informative. So that's multi-comparison correction on the basis of family-wise error correction, peak level correction, whole brain. And you can see the map is quite significant. Does it tell you? Yes, so it tells you the height threshold here is 7.025. So you could equally go into XJ view and open the image. Again, we take our SPM T maps. Remember, we've done a contrast, which was activation. So we got a beta, which is the map for the fit of our mean, and then we do a contrast. So in our case, it was a 1, and that gives a corresponding T map. Okay, so these are the regions that are activated on average. And you can see there's blue regions as well. These are regions that are deactivated on average, but without any thresholding. So next thing we want to do is we want to apply the threshold. So we can set this here, it's this T map, to 7.025. Let's say 026, and that gets rid of it. So that's our map corrected for multiple comparisons, because you've taken the same value. Let me just set this to 0. Okay, so we could do that. And that way you can just take the crosshairs away, like that. Just clicking here to get rid of the crosshairs. Now, this seems like a very small map, but actually, for anything to survive this level of correction is quite significant. Do slice view again, rendering again, like that. Click the report, and you get out 6 clusters. And the first cluster is the cerebellum, and it's 61 voxels in total. 647 of them is in the right cerebellum, 454 in the cerebellum anterior lobe. That gives you information you need. Labeling is a little bit of a dark art, has to be said, because we are spatially normalizing the data, and there's also some of the sources of issues. And this smaller one. So again, you can see middle frontal gyrus, superior frontal gyrus, kind of on the boundary of those two. And that gives you basically the regions. So you can right-click on X-ray view and get out some indication of the brain labels. And obviously then you can click slice views. So let's say 3 by 2, 2 rows. I'm going to make spacing a little bit bigger, so let's say 8. Let's say set this to 15. Let's say 3 by 3. There we go. Or you can do a cross-section, transverse, anything like that. Okay. So that's just to show you X-ray view. It's quite useful because you can do things like get rid of the crosshairs, which drive me crazy. Again, you save the figure as, whatever you want. You can also save these blobs out as images, so that's why you can apply a threshold here and then save it there. But you already can do that within SPM, so it's not such a benefit. Okay, so that's peak level correction. Let's have a look at cluster level correction again. So in this case, set significance level change. We'll say none. We pick our cluster forming threshold, which is 0.001, and we have an extent threshold of 0. And again, we now go through here and we find all the significant clusters. So 0.071 isn't significant, 0.084 isn't, but 0.034 is. Okay. So these ones are ranked in terms of the amplitude of the response, the peak, T statistic. So that's why these ones are not significant, but they're higher up than this one. That's important to note. So the smallest significant cluster that I can see is this 454. So that'll be our extent threshold, 454. So significance level change, no. Set cluster forming threshold same, 454. And now we have a table that's corrected for multiple comparisons, like that. Okay. So previous sections. Right. So hopefully that's very clear. The last thing we'll do is, let's say you want a specific hypothesis you want to test. You want to test whether the basal ganglia is recruiting, and we can see it is, but let's just test it anyway. So we'll go back and set thresholds uncorrected. So we're going to apply peak level correction within a mask. So in that case, I mean, technically you could go down to 0.05, but there's no point. I tend to do 0.01 or 0.001. Because you're going to apply multiple comparisons correction on the base of response amplitude, so it kind of doesn't matter what cluster forming threshold. But if you set it too high, things will disappear that might have survived correction. So we'll set it 0.01 for now. Click small volume, image. You go up to your ROIs, which is 2 levels up, basal ganglia, and there you go. And remember, it's this column here. And it's kind of, when you do a small volume correction to test hypothesis, it's kind of a binary. You don't really care, I mean, unless they're in the opposite hemisphere, which they are in this case. But otherwise, it's just a yes, no. In this case, we've got, yes, the answer is yes, definitely. We have a peak level corrected results, which is what we want. You'll almost always have cluster corrected because your ROI is small with respect to the independent units within the image. So the likelihood of a cluster, if there's any cluster, it's likely to extend beyond the boundaries of your map, your ROI, so it's going to be significant. But here you can see there's also one in the other hemisphere. So in that case, because we've used a bilateral mask, you might want to report that there's an effect in both, a bilateral effect within that region. Okay. So that's multiple comparison correction on the basis of peak response, whole brain, cluster response, and small volume correction, which is always peak level, not cluster-based correction. When you're playing around with thresholding and all this sort of stuff, it's always important to pay attention to this number here, because sometimes you go back and you think you set it back to 0.001, but it's held on to the number of the voxel threshold that you used previously. So the cluster extent threshold you used previously. Okay, so with that, let's move on to do a two-sample t-test. So we'll move up. So move up one directory. So change directory, space dot dot. Make a directory. Nope. DR. Two sample. T. Okay. So in this case, again, specify second level. Go to your batch editor. Design, you pick two sample. So the scans then here are we going to take in placebo for the first group. Done. Oh, sorry. Two sample t-test in design. Okay. So you can see now we have two things again. Remember, wherever there's an X, you need to put some input. So go into placebo 1 for the first group. Right click, select all. And go into scans for group 2, specify drug 1. So we're going to drug 1 in this case. Drug 1, right click, select all. Only 16 scans. Now here the groups are independent of each other. They're not related measures. There's two separate groups. And the variance is unequal. We're assuming they're drawn from different populations. Now as it happens in this data, this is incorrect. This is the same subject scanned twice. But the reason I'm doing it this way is you'll see the difference in how the model, the level of significance we get by treating the data in the wrong way. You'll see the effect is very, very weak here, but then we model it correctly as a repeated measure with a paired t-test, the significance is much higher. Again, you can put in nuisance regressors or whatever, but again, not for fMRI primarily. But you can control for things like the grand mean and stuff like that. So one of the things often happens, perfusion is another example like this, where you need to test the effects with respect to the overall global signal. We don't do that in fMRI. Again, the signal itself isn't quantitative. It doesn't mean anything specifically, whereas in PET, it's kind of a measure of the radiation or blood flow. Same with perfusion maps, or same with VBM, where it's a matter of grey matter content. Okay. So again, covariates is the same. Multiple covariates can be loaded as a text or mat file. The masking is the same. And these parameters. So basically, the only one you sometimes want to do is covariates or the masking issue. We'll add on, again, model estimation, set dependency, and then we'll save this as two sample. And we'll press play. And I will pause it there and come back once it's... Okay. Yeah, still recording. Great. Okay, so you can see here again the model estimation is completed. So let's have a quick look at the results. So as you see, it'll be the same as always. We click on results, go into two sample, click on the spm.mat. Now, here the design matrix is slightly different. We have two columns. This one encodes the mean for group 1, and this column encodes the mean for group 2. So there's two columns. So in this case, there's two potential, well, there's more than two contrasts, but we'll fix on two. The first is compare group 1 to group 2. So identify brain regions which are more activated in group 1 than group 2. And the other one is to identify brain regions more activated in group 2 compared to group 1. So we'll do both of those now. I can tell you now the results aren't significant. So we'll say group 1 minus group 2. So 1 times group 1 minus 1 times group 2. Yep, 1 times this one minus 1 times this beta. Yeah, that's fine. It's not going to allow me to do that. And press done. Let's pick that contrast. And now it's going to be asking me the usual things. So apply masking, no. Won't apply any correction yet. And you can see it's now written out the contrast image, con01, and the T image. So in this case, obviously, our design matrix had 2 columns, so there's 2 betas, 1 for each column. Then there's the contrast, which is the one we've just created, which is this one minus this one. We still have the res.s image. We have this SPM map for this contrast, and the spm.mat, and the bat file we saved. Okay. So as you can see, there's nothing significant in the cluster correction. There's nothing significant there. Now, equally, there's nothing kind of in the area of any of the regions we have in our mask. We could drop the threshold down a little bit and just see if anything comes through. So we'll say no. And we'll drop it down to 0.001. Sorry, 0.01. Oh, and we do start to see a little bit more, and there's something in this area here. So why do we now test our now, we'll do small volume correction to test if there's any evidence of regions. Now this is now significant, and this is a common issue. So the problem is we've dropped the threshold down a little bit, and suddenly now we have a cluster that's suddenly massive and really significant, although at one level up, at 0.001, an order of magnitude more stringent, there's nothing there. So there's always a temptation to drop the thresholds a little bit, but the evidence seems to suggest that you do increase the risk of false positives. So maybe this is a false positive. So it's probably best to be a bit more stringent. But for small volume correction, we're concerned with peak level correction. So actually, it doesn't really matter what height threshold we use. Although if you set it too high, there'll be nothing on the map to actually correct. So let's go up. Let's click post. And 0.138. So remember, it's always this one for small volume correction. It's still not significant. To be clear, by the way, when you're making tables for statistical results, the things you need to include are the K value, the T or Z score, and your coordinates, and a brain label. All the rest of the stuff doesn't need. Some people include the corrected p-value. I tend not to, but that's because the Z score kind of tells you that. But whatever. Great. Okay. And let's do the reverse contrast. So we'll say new contrast, and this time we'll do group 2 minus group 1. So it's -1 times group 1 and 1 times group 2. Press done, and it just quickly runs it through it. And again, you can see there's nothing there. Okay. We can always switch back and forward between contrasts. In the old days, you had to keep pressing results, but they put this in, which is quite nice. And that's it. And when you're switching back and forth, the thresholds don't change. So I think we'll leave that there. We'll move now to paired t-test, because there's nothing results-wise there. I mean, I can quickly run over overlaying again. So overlay, sorry, that's saving. Overlay sections, previous, canonical. Saving the map, saving binary. So saving all clusters as binary will give you one map with all these clusters on a single, with all of them set to 1 on one map. If you all clusters n binary, you'll get separate clusters as separate ROIs. Actually, let me show you that. So this is keeping them separate. So you get n binary array. So I've done this variable test, but if I now, so if I say little hat test, and I see how many, I'll say 1:1000 because I don't know how many there are. Oh, maybe there's only one. Oh, there's only one image, but the numbers are the ROIs are numbered differently depending on the region. So this one's 6 or 5. It's a bit hard to see actually on this one. So all of these blobs here are part of cluster 1. But there are some other clusters over here, like this one here, which is a value of 2.8 or something like that. They should be integers, but the numbers on the edges will be slightly different. Okay, so what we'll do now is we'll move and do a paired t-test, because we know we'll get some results. So it's the same data, but we're going to model it slightly differently. So we'll make a directory, paired t. And this is a bit of a pain to do. So we'll click paired t-test. Oh yeah, click on here, batch editor. So we clicked on specify second level again, and then design paired t-test. So we're going to model the data again. So directory paired, done. We'll add on the estimation bit now, just to get out of the way. Dependency. Okay. Now it's the same. We're going to model the same data, so placebo 1 and drug 1, but because the scans we're telling in this model, we're saying that the data is repeated measures. We don't load the data up for all the subjects for group 1 at time 1 and separately all the subjects at time 2. We load them up for each subject, so each pair is one person. So we click specify, go into placebo 1, select the first image, then go up one level, go into drug 1 and select the corresponding image, so again subject 1. So that's one pair. And there's 16 pairs, so we'll do 1, do the second get lot. So we'll do specify placebo 1, let's go subject 2 here. And you don't press done, you go again, pick 2. So we're going to do this 3 times. Let's do another one. So placebo 1, subject 3, drug 1, subject 3. Now I have no intention of doing that manually for all of those. Don't drive me crazy. But what you can do here is let's take subject 1 and let's replicate them. So that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Just run down here to see, so it stops at 16. If you put in too many, you can always just go down and delete the extra ones. So we stopped at 3. 3 was correct, wasn't it? So what we do is here, if we click on specify, you can see this is subject 1 now. We've replicated subject 1 over again. If you click edit, if you make this image bigger, oh no, sorry. Make this window bigger. So change this to subject 4. And we accept. So now it's subject 4. And we get to the next subject, specify, edit. This one will be number 6. This might actually be longer than doing it by hand. So I'm just going to pause this, and once I'm finished and got it done, I'll... Okay, is it working? Okay, great. So that's that done, although, so you can see all the way down to subject 16. I have a slight confession though. I wasn't going to do that by hand, so I saved it as a script and just did basically tweak those numbers there. You'll see how to do that when we get to the 4th lab, but so I basically just saved it out, tweaked those numbers, and then wrote save as a batch file. Okay, so once you've done that, we'll save it inside the folder we want to save it inside, which is our paired folder. Paired batch. And then we just press play. And again, I might pause it for a second. Okay. Okay, so I think we're back. The paired t-test model is finished. So we'll look at the results again. We go into paired t. Oh, sorry, no, into paired t. So this, just to tell you, so this basically, let's review this actually, sorry, review. Okay, so these are the scans for each subject. So here's one, these columns here are the subject means. They represent the average response of the subject, average over the two conditions. So they kind of calculate, they basically mean center the data in essence. But the between subjects variance is distributed over these columns here. And then we've got condition 1 and condition 2. Okay? And then for the first subject, then condition 1, condition 2 for the second subject, condition 1, condition 2 for the third subject. Okay? So when we want to compare these conditions, it's just going to be 1 times the condition 1 minus 1 times condition 2, or the converse. However, if we want to look at the individual response to one condition, we would need to weight the contribution, because the response on average across here is some of the response for that condition in isolation is distributed over these, because remember we've taken the average of these two and taken it out. So in that case we may want to put them back in, and you'll see why that's important later on. I'm going to show you. But let's begin by doing the standard contrast. So pair t-test, let's compare. So we go condition 1, let's actually, in fact let's just do placebo, because they are placebo and drug, greater than minus drug. So it's 1 times that minus 1 times that. And because this is something, we don't need to worry about these columns. They're just modeling the between subjects variance, because with the repeated measures we don't care about between subjects variance. We only want the response within each subject on average. So again, no contrast, no results, threshold is the same. And there you can see. So this is the map here for the placebo minus drug response. So just compare that quickly to the 2 sample t-test with the same data. So same height thresholds, results far, far weaker. Okay. Let's go back to pair t-test. Okay, so we can see is if we did family-wise error correction, peak level corrected, we will certainly have one result. This one wouldn't be significant, it's 0.063. So let's do that to begin with. Contrast significance level, set to 0.055. And that is 2 voxels, but it's significant. Now Carl Friston, who created SPM, would say even 1 voxel surviving family-wise error correction across the whole brain on the basis of peak response peak or response amplitude is worth bearing in mind. But I think a lot of reviewers would have problems with it. But you often see people showing displaying the uncorrected map. So, and I would do the same thing. I'd show it, and I'd say for illustrative purposes, the images are thresholded at 0.001 uncorrected, but the results survive multiple comparisons correction. Fine. Okay, so hopefully that's okay. Now, here's something we haven't done yet. So if we plot the response, contrast estimates and 90% confidence intervals, I get a bar like that. That's not really that informative. Okay, I'm going to go back to the paired t-test first, sorry, the 2 sample t-test, and just show you how to plot results before we do it in the paired t-test. So let's go to here, and we'll set the threshold a little bit lower. Okay. And if we right click here, go to global maximum. All I've done here is just gone to the top peak in the 2 sample t-test contrast. We know this is not significant peak level. If we plot the response of this contrast, we get a single bar. Not hugely interesting. But what we really want is to be able to plot the 2 separate bars. Now the key thing about the contrast, when you plot contrast estimates and 90% confidence intervals, is it gives you 1 bar for every row in your contrast, and our contrast here was 1 space minus 1. So if we want to be able to create a new plot 2 bars, we need to have a contrast that has 2 bars. It's on 2 rows. So let's show you what I mean. So when we do this, the plot here is this 1 space minus 1. So we get, when we plot it, we get 1 bar, which is the magnitude of the difference. But if we create an F contrast, it allows us to do something slightly different. It's called the effects of interest contrast. And it's something that used to be created in SPM by default, but it's gone. But it was quite useful for plotting. So if we do 1, 0, 1, we're asking, show me any brain, it's an F contrast, so it's bidirectional. Are there any brain regions which respond during condition 1, group 1 basically, or respond to group 2? I'm not comparing them here. But the key thing is this contrast has 2 bars, one reflecting the first column, and the second one reflecting the second one. So when we plot this using this contrast, we'll get the 2 bars that we want. So you can see, saying 1 over this column, and separately 1 over this. So this will show us any voxels that are activated or deactivated by any of these two, either of these 2 groups. Now, it's a very liberal contrast, so you get a huge amount of stuff coming through, because we're just basically asking, is there anything here, up or down, here or here? We don't actually care about the map, okay, because it's very non-specific. Just tells us these are voxels where something's happening, but not telling us what that thing's happening. They could be recruited, suppressed, different between the 2 groups, who knows. But what's useful for it is we go back to our original contrast, and we plot our contrast estimate. We plot our group 1 minus group 2, we get a single bar. But if we plot again, but this time pick the effects of interest just for plotting, we're not using it to threshold the map. We now get 2 bars. So you can see for all motor greater than control, which was our contrast, for group 1 there's more activation in this region for motor compared to control, but for group 2 there's greater response during control than there is during all motor. Okay, so that's the contrast allows us a quick and dirty way to get a sense of what's going on. Okay, so let's go back then to the paired t-test. And what we'll do is we'll create the same thing. The problem is, because of these subject columns, I can't just put a 1 here. It won't work. So if I want to do 0, 1 like we did before, it just won't work. Because some of the signal which is responding to just one condition by itself is actually distributed over here. We've used this to subtract the mean from these 2 images, but if I want to look at the average response, I need to put that mean back in. So what you can do is you skip over the second condition, and then each one of these subjects, because there's all of these, contributes 1/16, so 16 subjects. So it's 1 for every subject, 1/nth for every subject, in this case 16. So we can say 1 comma 16 divided by 16. So this will give us basically 16. So you can see there's a slight variance in shading here. So just to show you what that looks like. 1, 0, 1s, 1 comma. You get 1, 0, and then 0.0265, 16 of them. So it gives a total number of columns of 18. Okay? So we can use that then to create a contrast that allows us then to plot the response from the 2 conditions in the paired t-test. 1, 0, 1s, 16. 0, 1, 0, sorry, 0, 0, 1s. Okay, so you get 2 columns, the mean over this one and the mean over this one. It's basically one's up or down, because it's an F contrast bidirectional, and I'll call this the effects of interest. And again, it's a very, very unconstrained contrast. Anything non-zero basically in either group will appear on it, so it's massively significant. We don't care about that. Let's go back to our initial contrast. So let's go to our peak. If we now plot contrast estimates and 90% confidence intervals for our contrast, placebo versus drug, we get 1 bar. Remember, we're using this map to find the region we want to plot, but when we plot, we pick the other contrast. Effects of interest. Okay, and that's what we see. So remember, this is adjusted now with respect to the subject column, so this brings it back. A slightly different coordinate as well. This region's basically probably only marginally more activated in control than during motor, but on the drug, there's a much stronger, well, either much increased response in this area during the control condition, which is probably what's actually happening, or massively reduced activation of the motor task. It's the cuneus, so it's probably what's happening is the drug's enhanced the control-related activation here, which is probably to do with attentional mechanisms. And that's it. So that's basically the response for plotting. Again, so that's quite a useful contrast to have. So again, we'll overlap previous sections, look at bars. Whole brain gives stats. So again, we've done peak level correction, but if we want to do cluster level correction, again, we have to look here. So this is significant. This is significant. I can't see anything else significant here. So and this is 2291, 969. So there's nothing else. So 969 is my cluster is my extent threshold. 969. So if we say this to change, no, leave that alone. And then 969. This is now our map thresholded on the basis of cluster extent. Okay, so I think that's the key part. We've overlay, you can save, you can plot. Let's have a quick look at the setup of the other models, but I don't think we're going to go through them unless people want to during the lab. So if we go back up into models, for the one-way ANOVA, it's like the two-sample t-test, except instead of two groups, you have, they say cells, but in essence they're groups. And again, their independence is yes, variance is unequal, because they're drawn from different groups. All of this is the same. Now, if you want to put a covariate where there's multiple groups, you have to put the covariate in the same order. So obviously all these 16 scans will be first, then all these 16 scans, then all these 16 scans. So what's 3? So 30, 48. So it'll be 48 values in your covariate if you wanted to control for something. If you look at the one-way ANOVA within subject, however, it's like a paired t-test, except instead of labelled as pairs, they're labelled as scans. And in this case, we're saying 1, 2, 3. There's 4 of them we've put in here, and you have to tell it. So the reason for this is because if someone's missing a scan, let's say this person only had 3 scans, but some of them had 4. And they were missing scan 2, we could just say 1, 3, 4. So it knows then how to adjust the model accordingly. Okay. Then there's multiple regression models, which are pretty straightforward. It's just basically a one-sample t-test with a nuisance covariate, with nuisance covariates. So here you got scans, like a one-sample t-test. And then you put in your covariates. And you can have basically mean centered over the whole group or not. Generally, you would mean center over the whole group, but it depends. So there's a very good website, Mumford covariate mean centering. So this website here, so Mumford covariate mean centering, explains when you're doing a model whether or not you should mean center. So if you want to control for a covariate when you're on a one-sample t-test, is mean centering yes if you want to test the response for the subject, the mean. But if you want to test for the correlation with your covariate, then no. But if you want to look at the response on average while controlling for this, then you should mean center. Although it doesn't mean centering the covariate will never change the contrast estimates. So it's fine because the intercept is modeled. Here, if you've got two groups, but with a nuisance covariate, so let's say IQ or something like that, if you want to look at the difference between the groups, you shouldn't. You don't need to. If you want to look at the covariate by itself, then no, you don't need to. But if you want to look at one of these in isolation, so here you can see just this one or this one, then yes, you should mean center. Does that make sense? If a model like this, which is a really more complicated, where it allows you to test for the interaction of the slopes, you've got the intercept for group 1, the intercept for group 2, the covariate for group 1 with zeros then, and zeros then covariate for group 2. If you want to compare the response to these two conditions with this kind of weird controlling separated, then yes, but it's not really very wise. There's not really much reason why you'd separate this or split this covariate into an interaction term if you didn't need to. But if you want to test for the interaction of the slopes here, like this, then this last one says no. Okay, and that's definitely worth having a look at for multiple regression models. So it's just mumford.fmripower.org/mean_centering. And the last two models are flexible factorials and full factorial. So full factorial is kind of like an extension of a one-way ANOVA between groups. So you have multiple factors. And so let's say in this case group, and we say there's two groups, and they're independent of each other, and they have an unequal variance. And the other variable is time. Now, time is actually a repeated measure, so you can say they're not independent of each other, and the variance is equal. But for real repeated measures like this, it would much better to do a flexible factorial model. So, however, if this was a betweens group variance like genetics, so the two groups of comped polymorphism or ApoE or something like that, and you could say we've got homozygotes of the meta allele, heterozygotes, and homozygotes of the val allele for comped, then you'd have three levels here. And then you build your cells, and this is just a standard ANOVA. So this is the first level of factor 1 and the first level of factor 2, and you put all 16 scans that correspond to that in here. The first level of factor 1 and the second level of factor 2, so this is the next genotype. All the subjects go in there. Then the second level of factor 2, so this is the second group, but the first genotype, for example. Or the second group, second genotype will go in there, for example. Okay? And the final model, and this is explained in the SPM manual, pretty straightforward, and the contrast then would just be, I'll show you that in a second. So yeah, so if you've got a 2x2 model and you want to compare the so if you want to test the main effective group, so say it's group, then it'd be group 1 plus group 1 minus group 1 minus group 2. So we've got 4 cells, group 1, time 1, group 1, genotype 1, group 1, genotype 2, group 2, genotype 1, group 2, genotype 2. The main effective group, would be this. So you're saying, I don't really care about the genotype, I'm just averaging over the two genotypes to find the main effective group, the main difference between the two groups, ignoring genotype. If I want the main effective genotype, it'd be 1 minus 1, 1 minus 1. So in this case, these are F contrasts, or they could be T's. You have to do the reverse as well. So it's saying, show me where it's greater for the met compared to the val allele, average across both groups. If you're doing as a T contrast, then you need to do the converse as well. But as an F, it's bidirectional. And the final thing is the interaction. So this is where the difference between val and met. So we have this as a group comparison. So this is the main effective genotype. And then we have this as the main effective group. If we multiply those two together, we basically get this. Anyone who's done psychology will know that this ran over the contrasts and how the cells combine. But that's basically it. I'm happy to go over that if people have questions. We can do that if time permits. I'm sure time probably will permit in this lab. So the last thing then is the flexible factorial, and this is a much more complicated model. Where's the batch window gone? Batch. Oh, sorry. Load up the models. Flexible factorial. And this is basically repeated measures design where you've got multiple factors. But here you can build the model any way you want. You can say you specify it in the special variables like subject. But this all relates to the internal structure of the model. And then you build the factors you actually want to include in the design matrix here, main effects and interactions. So if you're interested in doing a flexible factorial, there is another website, or I should say a PDF. So Gittelman, contrast, flexible. Contrast weights in flexible factorial design. This actually tells you how to set up a flexible factorial design. It's a really, really good document. Actually takes you through the whole process of setting up the design. They get one thing wrong. When you use this model with these columns here, in the model, the main effective subject columns, it's inappropriate to test for the main effective group because the between subjects variance is being explained by these columns. So if you take average, do main effective group, let's say this isn't a good example here, but so here we go, 2 groups. 3 conditions on group 1, 3 conditions on group 2, so repeated measures, and we're controlling subjects. Some people will say, oh, well, look at the main effective group, so they'll say 1, 1, 1, minus 1, minus 1, minus 1. The problem with that, and that's what they explain here, that's the contrast they would say. Main effective group, they use a slightly complicated formula to make it, but in essence that's the contrast. And the problem with that is that the between subjects variability, which is the error on the estimate of the group mean, is explained away. So what you have is estimates of group means with 0 error, and so you get massively inflated t statistics. But anyway, if you're interested in that, it's contrast underscore weighting underscore Glascher, GLASCHER underscore Gittelman underscore 2008.pdf. But if you just Google contrast, flexible factorial contrast weighting or whatever, I did Gittelman contrast flexible. That was enough to find it. Okay. The only other thing I should say to you about these things, if I go back to my paired t-test or 2-sample t-test, let's say, contrast, 2-sample t-test, is it is possible to do the contrast definition automatically, which we didn't do in the 2-sample, even in the first level models. But you can just do SPM contrast manager, pick the SPM.mat. So again, we'll just use a dependency, and then you can specify t-contrast. It just asks you for the name, so in their case we say group 1 minus group 2. And because we know the structure of the model, it'll just be 1 minus 1. And you can do this also when you do your first level models. You can build in your contrast directly into the SPM.mat. So just to show it to you, continue. So if we go into one level analysis, pick your model batch. So again, here we have 4 conditions, so we kind of go stats, model, contrast manager. And then we'll say we'll create two contrasts we've used before. So free minus queued, and all so we know the free was the first column and we know queued was the second column. But if we want to free greater than control, we just put a 0 there. So we just multiply that beta by 0. So what I'll do is I'll just do that quickly. 1, 1, minus 2. And let's just create the other ones as well quickly. Create 2 new T contrasts. The other thing to say to you is, which one's this? Is this name? Oh, yeah. So we'll say free greater than control. T contrasts are bidirectional, so when you do the subtraction, if there's a region that has a response which is more in the control than in free, it'll just have a negative value. So the image actually contains that information within it. Queued minus control is 0, 1, minus 1. We'll say model batch with contrast. And I think that's probably it. Okay, if there's any queries, I'm happy to hang around and talk more. If anyone has specific queries about other models, we can talk with them now.